Hi everyone, good evening. I am Apurva and this is week 6 for games and information. So, let's start with the tutorial. There was one question that still needed to be answered from one of the previous quizzes, so I'll start with that. Yeah, Vivek is here. Okay. Right. So, it was this question. This was, I think, assignment 2. Question 3. So, in this question, we are told that the event where Rima has won is E. It can have more than one states, or rather, this is the event. This event basically says that Rima has won. So, any of these states which belong to this one would represent that she has won. So, because we want to find out from this, we want to find out which particular state of the world from these has this kind of a property. So we need to first of all consider one of these states itself. We cannot consider omega 2, so that is by default out. So these are the options. Now what we are required to do is, first point is Rima won the tournament, which is basically saying that our state of the world omega should be something that lies in the event, because event E represents winning. Next thing that we want is that Apurva knows that Rima won the tournament, meaning the knowledge operator for Apurva of the event E should be such that whichever state we are talking about should belong to this state. Okay, that's point number 2. So this is first and this is second. And this is the last part. This is the key. Now, Rima should not know that Apurva knows. Meaning, we can either write it like this, that the knowledge operator for Rima, that Apurva knows the event has occurred, will not include the state that we are referring to. That's it. That's all we're supposed to do. And we're supposed to find such a state which satisfies all these 3 properties. These 3 properties represent 3 different parts of the problem itself. Okay, so last time we had gotten till here. It's just this last portion that was remaining. Okay, one mistake. This is saying Rima does not know, so this is not going to belong to Rima's knowledge operator of knowing what Apurva knows. Okay, so let's start this way. Let's take one at a time. So these are the options, I believe, 3, 4 and 5. You must have already seen that the correct answer is this one. So let's start the opposite way. Let's start with W3. Let's say the state of the world is W3. Now the first condition is satisfied. W3 does belong to the event, meaning Rima has won. That part is true. Second thing, let's look at 2 things now. The knowledge operator for Apurva for this state, which is just looking at every partition and just comparing if that partition, a particular part of that partition, is a subset of E or not. So that means omega 1 can be included. Omega 2 cannot be included because this set can't allow distinguishing 2 from 3. As in, Apurva cannot distinguish between these 2. Hence, this partitioning cannot be included in the knowledge operator. But this and this can be included because these form a subset of E. So, this is 4 and 5. Okay, now from here we can already see that this does not include the state that we are considering. So, this is wrong. So, we don't need to check the next part. Okay, so this state is not an option. Now let's look at if the state of the world was 4. So up till here it's true, it's included in E. Knowledge operator of Apurva for this event will include 4. Yeah.
Actually, W does not belongs to the knowledge operator of E. That is true, no?
No, we require that this state of the world should lie in the knowledge operator of Apurva, because Apurva knows that Reema has won. So she knows that the event has happened, meaning the winning has happened, is aware. She's aware of that. So for her, this state of the world, which is what is representing that she has won, should be something that's known to Apurva. So in that sense, it should be known. This is what we require, but that's not satisfied by omega 3. Right? Then you can look at omega 4. So omega 4 satisfies first 2 conditions. That is fine. Now let's look at Kr of Ka of E, which basically is saying we are looking at Kr of omega 4. I think omega 4 is a separate part. It comes with 5. Okay. Now this is a subset of Ka of E, right? Knowledge operator of Apurva for the event E, meaning this can be included. So Kr of Ka of E will allow 4 and 5 to be included, but this includes 4. So in this state, what is happening is Reema knows that Apurva knows that Reema has won. That's not what we want. We don't want Reema to know that Apurva knows. So this, because this last condition is not satisfied, this is not the state that we are looking for our conditions. Exactly same thing will happen if we were to take omega equal to 5. It will be exact same arguments. So now I'll finally come to the last one. You can already see what's going to happen here. For the last one, we know Ka of E is, but Kr of this state of the world, omega 1, is actually 1 and 2. Yeah. For Reema, 1 and 2 are indistinguishable. But this event does not include 2. So this is not a subset of this. If this is not a subset of this, then Kr of Ka of E will not include omega 1, or rather it will be 4 and 5, which does not include omega 1. So because it satisfies all the 3 conditions we required, the first one, the second one, and the third one, that's why the answer is the state of the world should be this one.
It's very clear. Thank you so much.
Yeah, sure. Okay, so alright, let's start today's tutorial. Before we do that, let's take a quick recap of what we have been talking about so far. So far we have been dealing with games that can be represented in games where the payoff matrix can be represented in the form of some or the other kind of a matrix. If it is with finite strategies, if it is not finite, then it might be some interval and so on. So for games of these kinds, let's say we have some players, some actions available to them. These types of games where we represent it in the form of a matrix, what we are actually saying is player 1 or player 2 for that matter does not know the action taken by the other one. So it's like they are taking the action at the same time, and then the outcome is revealed to both of them together. Time is not the more important part here. It's that they don't know what is the action taken by the other one. Yeah, so these are called simultaneous games. Okay, something might be here, that doesn't matter. The key point here is P1 will not know the actions action taken by P2, and similarly the other way around. So P1, P2, P2, P1. So let me take an example. So suppose we consider a game like chess, or a game like rock, paper, scissors. I've probably written the spelling of scissor completely wrong, but please ignore that. So let's talk about both of these games one by one. In a game of chess, for example, the players have a sequence in which they take their turns. So player 1 takes their turn, player 2 can see what was done by player 1, and then it takes its turn, and that sort of goes on. So there are two things here. One, this is not a simultaneous game. Such games are called dynamic games. And on top of that, this one is a repeated game where a kind of a pattern is continuously going on. What about rock, paper, scissors? Let's say it's happening only one time. Is it a simultaneous game or a dynamic game? Exactly, it's a simultaneous game. Oh, there are others also. For example, the one that we saw earlier about rabbit and deer, or matching pennies. This last one, I can't recall the name for this game, but where the troops are to be divided, which location the troops should go to. All of these are simultaneous games. So from this lecture onwards, we are going to start talking about games which do not have this structure anymore, in the sense that the players will know the action taken by the previous player. So let's take the first example that was taken in the lectures also. So let's say, suppose there are two firms who are both selling some products. The products are homogeneous in the sense that it's only the quantity that matters. The brand and the quality is sort of like standardized, and there's nothing to be done over there. And the pricings are dependent only on the quantity, quality and all doesn't matter. So in that type of a situation, let's say there are two scenarios. We are taking the case where both the firms are choosing their quantities independently. They don't know anything about what is the quantity chosen by the other one. In what quantity they are preparing is not known. So let's say this is the scenario. Qi refers to that quantity for each of the firms. So let's say there are two firms, so it's Q1 and Q2, and the pricing, let's say, is defined in the following form. This is the price of the goods. Then the utility function for each of the players would be something that will depend on the price of each unit times whatever quantity they prepared, and from there they'll subtract the cost of preparing that quantity. Here we have sort of assumed that the cost of preparing that good in either of the firms is the same, so it's a constant value and it's a common C. So in such a game, what is happening is the two firms are now supposed to decide what quantity should they prepare, in what quantity should they prepare the goods. So they can, in one extreme, they can be like, okay, I'm not going to prepare anything at all and let the other person handle it. In that case, it will not have to worry about either of those scenarios. So it will not have a cost, it will not gain anything either. So that's a complete extreme situation, so it will not get a payoff. So they'll be like, okay, let's start creating the quantity in some creating the goods in some amount. So then they'll start incurring some price because of that, and will also keep getting some sort of a payoff. Now whether this quantity, this payoff is overall positive or negative depends on what was done by the other player, what was prepared by the other player. It can so happen that this becomes exactly 0, or this can have some other values. That's also possible. If this becomes exactly 0, then they're not getting any benefit, and they're just losing money in the process of creating goods. So now they're supposed to decide how are they going to figure out how much to produce. So this posed as a game. By the way, this is still a simultaneous game. So what we're supposed to do is just, let's say both of them are maximizing their pay, or the utility, which basically is their profit. So they're trying to maximize this quantity, so they'll just take the derivatives and equate that to 0. So for player 1, they'll get q1 plus q2 minus c equal to 0, and similarly for the other player they'll get and once you solve these two equations together for optimal q1 and q2, you will get that they turn out to be this way. So in this particular example, what we have is, so in this particular example, what they did is the choice of q1 and q2, these are the strategies, or pure strategies if we want to call it, because these are continuous, so pure is all we're going to focus on for the time being. So the values that this q1 or q2 can take is in the range of 0 to infinity, and that's true for both of them. So this refers to the space of strategies for them. Which is a very specific kind of a space, and we already know how to deal with these types of problems and how to find a solution for these types of games, which is exactly what we have done. Now that's scenario number 1. There's also a possibility that one player knows what was played by the other one. So for example, let's say this is the second case where player 2 can observe what player 1 has played. So let's say player 1 has played in the sense what quantity it created. So let's say it created quantity q1. So now player 2 knows this quantity, and then it is supposed to figure out in what quantity should he be preparing the goods in his firm. In this case, this is no longer the same situation as before, because now that he knows what the other player has played already, he's possibly in an advantageous situation. All he has to now do is adjust the utility, adjust his own quantity in such a way that he at least maximizes his own utility. And here there's now a difference between what a strategy is and what action is. So let's specify that part carefully. So now whatever he gets, like whatever he decides to play, q2, like the realized value, we're going to call that as the action. But what we say is this is chosen using a function, so there's some function that looks at the value of q1 and then chooses what to play. That's what player 2 is doing. So this gamma 2 is what we call as strategy. This is the strategy for player 2, and this gamma 2 is a function from, for this example, is a function from 0 to infinity to the interval 0 to infinity. And here q1 serves as some information he did not have to begin with. This is the information he has gotten in this kind of a game. Now, if this is the scenario, the question that we could ask is, how are we going to talk about the solution of the game? How are we going to say whether that information is to be used or not? Whether that information makes the game or the solution of the game or the outcome of the game superior or not. So typically when we are dealing with just one player games, or games where a player is playing with the environment, who's not intelligent, who's not creating any strategies against our player, then knowing more is always beneficial. But in these kind of scenarios where there are two players, it's always possible to find games where knowing more does not necessarily mean that it'll give you an advantage. And it's also possible that knowing more gives you an advantage. So both the scenarios are possible. So what to do with the information becomes a very important question in games with multiple players. Okay, so to talk about this kind of a game, let's first talk about the strategy space for both the players. Now, nothing changed for player 1. Player 1 is still choosing how much quantity to produce the goods. So that stayed the same. So the strategy space for player 1 is still the same, which is we could denote it by gamma 1 if we want. So gamma 1 could be something that gamma 1 of, no, let's not do that. So q1 is something that still lies in this interval, and that's the strategy space for us, for player 1. But for player 2, he's now choosing the function based on which he should find what action to take. So for him, it is this function. Where gamma 2 I could have written the space of strategies for player 1 in a similar manner and called it gamma 1. So gamma 1 is any q1 such that this q1 belongs to the interval 0 to infinity. So now in this scenario, what will the two players be doing? So in this scenario, the two players will be taking their decisions anticipating that the structure of the game is the following: that there is some information that is known to player 2, but player 1 does not have a symmetric information of a similar kind. So here player 1 does not know what action was taken by player 2, but he can anticipate, knowing that player 1 knows, knowing that player 2 has information about player 1's action, what kind of an action should he take so that he redirects player 2 to go towards an outcome he wants. So he can do that kind of strategic thinking. So in such a scenario, we would say, let's denote it by these stars, double stars. So player 2 would have some action taken q2 star, that would be termed as the optimal action if it maximizes the utility for any value of q1. So we should also write for any q1. So all that this is doing is, this is taking this function q2 star, which takes in the value of q1 and produces an action out of it, and we just want this to match. So it's looking for a function. So in a functional sense, this solution is looking for a function that is going to maximize this object, or is going to be such that the action maximizes this object. Both of those are similar kind of statements. Now player 1 would know that player 2 would have done something like this. Player 1 already knows what q1 is going to choose, or what q1 it should choose. So let's say it knows the best q1, and it can also do this back calculation, figure out what is gamma 2 star of q1, what is that maximizing function gamma 2. Because it can do all of that, what it will now do as a strategic response would be to find a q1 star such that for him it's his utility that gets maximized. So here he's maximizing over q1, and he can find exactly what this function will be. And that's what he maximizes. So what this is ultimately doing is, both of their actions are a best response to each other. So this q2 star double star, this is a best response to any q1, or rather I should not write it like this. Whatever is the output of gamma 2 double star for any q1, that is the best response for any q1. Meaning if here we were to plug in q1 double star, then that is again a best response. And also q1 double star is chosen in such a way that this is a best response to the function gamma 2 of any q actually. So since they are both best responses to each other, this can be argued that this is a Nash equilibrium. You can do this argument more formally, but in a heuristic way this suffices. Okay, so a little bit more to go through this point, and then we can take a few more examples. One example from the lectures itself, and a few more other examples to get a good idea of what is going on in this week's work. Okay, now another thing to notice over here, we already noted that strategy and action are not the same if we are talking about dynamic games. In dynamic games, the realized outcome, the realized action is what we are referring to as action, but the plan of what to play given what information they have, that is what we are referring to as strategy. So at the start of the game, before the game starts, before any realizations are made, what we would be coming up with would be the plan. So this is done before the game. Strategy is chosen or decided before the game. But the action, as in the exact value of q2 or q2 double star, it depends on what realized value was taken by the other player. So it depends on this realized value. So this is during the game. And this difference between when strategy or action is decided allows us to just lift the problem from the level of actions, which is what we have been doing so far, even though we've been calling it strategies, and now in case of dynamic games, talk in terms of strategies, because strategies are still things that are decided before the game starts. So it is still something that is pre-decided. Once the game has started, the strategy is fixed. There's no changing that. So in that sense, we are calling this J1 and J2 as the utilities for the strategy. So this is the key part now. Once the realizations are found, as in we know what was the quantity decided by player 1, what is the quantity decided by player 2, and a strategy is also used on top of that, we would know the exact actions taken by both the players, and then we can actually calculate this as a number. So this side, it's mostly a functional thing. This side, it's a number that we are going to get once we have the realized values of the actions. So in this case, in case of dynamic games, Nash equilibria can be defined in the exact same way. Note this is defined for maximization. No player benefits from unilaterally deviating. So now in this particular example, what is happening? There is one player who is playing a quantity, who is playing an actual action, and the other player has a strategy plan. So what this basically now says is, the first point is saying player 1 will not benefit from changing its quantity, keeping the strategy of the other guy fixed. So unilateral deviation is not beneficial. That's the situation for first player, where Q is something that's going to lie in the simple range. So it's going to be in the interval 0 to infinity. What the other player would be doing is knowing that it has to be changing these functions. It's a search over functions. Nash equilibria says that if Q1 hat is fixed, and that is what we are calling as the equilibria of the game, if that is fixed, then the player will not benefit from deviating from this strategy either. Player 2 will not benefit from changing its strategy from say gamma 2 to gamma 2 hat. I've said it the other way around. It would prefer sticking with whatever is the Nash strategy, and that's what is happening. But here, what is to be considered is that we are talking about strategy for player 2, and for player 1, strategy and action are the same thing, so we don't have to worry about it. Which means we can now, at this point, we can formally make the arguments and say what we have defined here, the maximizations and the argmaxes that give us gamma 2 star and where is it? Q1 double star. These would form a Nash equilibria. So this is going to be a Nash equilibria. That's something that we already know. Another thing that happens is we had some equilibria coming from the simultaneous version of the game. So that was more like a situation where some information was missing. Player 1 took an action, but player 2 did not know what action was taken. So in that game, we still had a Nash equilibria. It so happens that a Nash equilibria in the simultaneous game would still be a Nash equilibria in this version of the game. It may not be a reasonable one. It may seem like it's not a good choice or an unreasonable choice, but it's still a valid Nash equilibria if we're going by this kind of a definition. So this is also true. In fact, this is a more general thing. This holds in general. So now let's start taking examples. So this was the example taken in class. I'll take this example only to just go through some of the definitions, and then I'll start taking a few new examples. Okay, so let's say we are given a game like this. Now this is what we call as a game tree. Each node needs to be mentioned which player is playing. From each node there might be some branches coming out, and there will be some actions mentioned there. So what is mentioned here, these are the actions. The plan as to which action to be taken, that's what we are putting inside a strategy. So here we have player 1 playing first, and then it's a player 2. So in this game, if we were to think of what is the solution of this game, by the way, both of them are maximizing, then one option is for the players to play R1, R2 respectively. So player 1 plays R1 and player 2 plays R2. That's one possibility. Why this is a possibility? By saying possibility, I'm saying this is actually a Nash equilibrium without formally going through it. The simple argument is we can look at it level by level. So for example, we can look over here and compare. This is player 2, so player 2 will compare the utility at this point, and it will say, okay, R2 is a better choice, and hence it would prefer playing that. So that means we can reduce this game and we could draw it in the following form. So player 2 has taken its choice, and this is what it has chosen. So this is what is finally left for player 1 to choose from. And between these two, player 1 would compare 1 and 0, and the maximizing option would be this one. So player 1 would choose this. So that gives us R1, R2 as one possible solution concept here. And in the process of doing this, you must have noticed what I've done is it's a recursive argument that I've made. And starting from the bottom, I'm starting from the last player who has to make a decision, so that the leaf nodes can be sort of pushed up. So this is the reduced version. This kind of process of trying to find a solution concept is basically assuming that there is recursive rationality, which is like saying that at each level, so here the player is deciding what to do, what is the best choice. If there were two options here also which were different, he would again be choosing which of these two is the best option, and he'd be choosing what he would do in either of those scenarios if he landed at this node versus if he landed at this node. So that's being recursively rational, and then that sort of goes upward towards the previous node and the previous player. So whatever equilibrium or a solution concept we get, we term that as a credible equilibrium or a credible solution concept. On the other hand, there is one more possibility. I'll directly get to it. Sir spent a sufficient amount of time on this in lecture, so I'm not going to go through it in full detail. So you could draw the normal form for this game. So let me say what I mean by that. So normal form means writing it this way, writing it in the form of a table. So let's look at the strategies this time. So strategy for player 1 is just L1 R1. There's nothing there. Player 2 has no strategy here, but let me not worry about that and just directly say strategy for player 2, it's to be defined at each stage. So this would be L2 R2. Meaning that I can put this information in the form of a strategic form, normal form game as follows. So this is player 1. Player 1 has L1 and R1, and player 2 has L2 and R2. Okay, so now this part is very much clear. If player 1 plays R1, then it has two options and there are two payoffs. So that part is very straightforward. So that I can just easily plug in here. Player 1 has played R2, and let's say player 2 has played L2. So this gives this as the payoff tuple, and for the other action of the player 2, this is what we would have gotten. Now it's this part that's unclear. Reason being, at this node, if player 1 had taken L1, there's nothing for player 2 to do. But we could say that player 2 still makes a plan what it would do, and hence it says, okay, I'll go with 0,2 here, and I'll go with the same outcome, 0,2. Even though this action option is not reachable from this node, it still plugs in those values in the normal form. And now what you can do is you can just find the Nash equilibria for this normal form. Remember, when we make the normal form, we have this assumption in our mind that what we are saying is player 1 and player 2 are making their moves simultaneously, that they don't know what the other person has played. So that's the reason why we just filled the same thing twice. Okay, so if now in this game we were to find the Nash and the players are maximizing, then we would get two options here. Okay, so one of those options is L1, L2, and the other option is R1, R2. We know R1, R2 is an option we would have gotten by using this recursive logic already. So this is fair, this is a credible option, this is fine. It's this option that's a little odd and counterintuitive, to be fair. This is something that can be interpreted as saying player 2 threatens to play L2 at, what's the name of the node? Y. If player 2 makes a threat that, okay, you know what, if you play R1 or if you reach node Y, I am going to play L2. If he makes that threat, player 1 would be forced to not reduce the game in this way, which is what he would have done the reduction as if he was assuming complete rationality from other player. He would be like, okay, so the reduction of the game now becomes, this is the argument from player 1's perspective, by the way. His choice for L1 would have given him 0,2. His choice of R1 would give him minus 1,1 if the threat was to actually materialize, if he were to actually go ahead with this and find out. And hence, he would be forced to compare 0 and minus 1. And between 0 and minus 1, he would prefer 0. And hence would end up with this as a equilibrium. But here, even though P2 is threatening to sort of deviate the game in the direction that he wanted, but there is no way for P1 to know for sure that if he had played R1, what would player 2 have actually done? Would he have chosen to stick with his threat or his promise, or would he have actually gone back and been rational and actually chosen R1? So an equilibrium that we would get in a situation of this kind is what is called as non-credible threat or a threat equilibria. So this is this one. This is this upper one. Okay, so in the assignment this week, there are a few questions of this kind where you have to find the threat equilibria. So ultimately, you're supposed to try and write the game assuming that there is this was happening in a simultaneous manner, or write the normal form of the game, consider all the possible strategies if there are more than 2, write them out clearly, and then find the Nash equilibria in the standard way we know. Start with pure. In fact, pure should suffice in most cases, otherwise you can go to mixed also. So yeah.
So I haven't yeah, sorry. understood.
Yeah,
So
yeah.
basically, I haven't covered the last lecture, but the normal form would be something like this: that this a graph that we have drawn, and then considered all the possibilities, like, or just a question.
Yeah, so this is the normal form for the above graph.
Okay, okay, okay.
We'll take a
Got
few
it.
more examples to to see how to make these normal form versions of any given graph.
Right. Okay.
Because you must have already noticed we filled in this value 0, 1 twice.
Mm-hmm.
If it's a bigger graph with more options, this becomes a little messy, but that's pretty much what you're going to be doing.
Okay. Okay.
Yeah, Vivek, you also had a question?
Yeah, actually, 1, 1 is the Nash equilibria, and 0, 2 is the thread of or non-credible Nash equilibria,
Yeah,
right?
yeah.
So those two are different always.
So this is more. This is what Sir was also saying in the tutorial, the lectures. This is more of a opinion. There's no consensus on this. If you were to think of this as a normal form game, both of these are Nash equilibrias. But if you were to think of this, this is actually an extensive form game or a dynamic game, then what you should be focusing on is something that's reasonable, something that can actually
So
materialize. So in that sense, people would prefer sticking with this one.
okay, so if for this game, if how many pure strategies are there? Means our answer is two, no? Two or one.
Uh, Typically, the question would specify how do they want you to answer it. So this one, I am just going to give the name. I'm not going to give the definition. This kind of equilibria where you're trying to find it recursively is called subgame perfect. And this one is our standard pure strategy Nash equilibria. So typically game any questions would ask you very clearly, tell the number of subgame perfect or tell the number of pure strategies. Okay, all right, let's take a few more examples to sort of get comfortable with this idea. Okay, this is an easy question. Okay, so let's start with this. So this is a question that is given a description, and it's asking make the. So we made this diagram above, right? This diagram. This way of representing a game is called extensive form. It has some rules. You'll get to know what the rules are for making it in a general setting, but for our purposes, this is still okay. So this question is just asking, given the description, make the extensive form representation of the game, and then also try the strategic form for the same game. So what this particular scenario is saying, there are two players, Eric and Sergey. So Eric is the one who starts. They're supposed to choose between two candidates, and the rules for choosing are this way. Eric makes a suggestion. So Eric has two options: either he'll choose Lee or he'll choose John. Then Sergey makes his suggestion. So he can suggest any of the candidates. So he can either suggest Lee or he can suggest John. Now the outcome of the game is decided by this last statement, which says candidates who receive the support of the two parties is accepted into the firm. So wherever it's a Lee situation or a John situation, like that's the chosen one by both of them, that's the one that gets chosen as the final one, or no one gets chosen. The one who gets support from both is chosen, or all the candidates are rejected. So these are the two possible outcomes. So here again no one gets selected, and here John gets selected. Okay, so this is the extensive form representation of whatever is described above. Now they're asking to also do this in the form of a payoff matrix, where they're saying take the payoff to be x and y, where these are just zeros and ones. 0 represents rejection and 1 represents selection. So this means if we were to write this in the form of a tuple, we can write it here and then put it in the normal form version. Let's say we write it for Leaf first and then for John. Okay, so this is the tuple that I'm going with. So this is 1, 0. Here nobody got selected. Here also nobody got selected. Here John got selected. Okay, so now if you were to make the normal form for this, this is the choice for Eric, this is the choice for okay, that's all. This question is not asking for a solution concept because the numbers are such that a solution concept will not help much. Okay, but you see how it is made. We're looking at the path, and then based on the payoff at the end of the path or at the leaf node, that payoff comes here. There can be situations where there is no path also, then how do we enter those values? That's the key part. Otherwise this is straightforward to convert an extensive form game into a normal form game. Any questions so far? Okay, if not, then let's take another example. Yeah. Okay, so let's say there's a scenario like this. This is very similar to the kind of problem that we had earlier. It's just the numbers have changed and maybe the meaning is slightly different. So there are two players. Player 1 is supposed to decide whether to enter a competition or a challenge or not enter. So it's an in and out for a challenge. And player 2 decides whether it accepts the challenge or it fights the challenge. And we are given some payoff values. And we're supposed to find the Nash equilibria in both the sense. So what we are calling as subgame perfect or recursively, and also by making the normal form matrix and from there. So threat equilibria and what we are considering as the commonly accepted one. So if you want to find the commonly accepted one, that's very easy. We would look at this game. Here first of all it's going to be player 2 who compares. So player 2 will be like, okay, between 1 and 0 I would prefer 1. Oh, by the way, both are maximizing. So it will prefer 1. So the reduced form of the game would be in would have, so this is like saying player 2 would prefer to accept in as comparison to fight if he gets to that, and since he prefers to accept, this is going to be the outcome player 1 would get if he had chosen in. So that's why we are pushing this outcome upwards. This is the other outcome. Now player 1 now just compares which is the better one for him, for his objective, which is to maximize. So he says, okay, this is the better one. That means the recursive way of doing it gives us in comma except as a credible Nash equilibrium. If we were to do it in the normal form version, so again, normal form, to be able to write the normal form, first you have to start with strategies. So let's say the strategy for player 1, well, player 1 has just two options, so that's in and out, so that's fine. For player 2, again, it's just two options, whether to accept or to fight. So now to write it in the normal form, we can fill out the simpler ones, which is, for example, for the path I and accept, in and accept. So in and accept gives us 2, 1, in and fight gives us 0, 0. So this is done, this is done. Out only has one outcome. No matter what is the strategy, which is just the plan, no matter what is the strategy plan for player 2, there's only one output. So it's the same output that will come up no matter what player 2 decides to do. And hence we would say that his payoff in either case would be just 1, 2. Then we can look at equilibria in
to
this.
solve for a okay, yeah, again, sorry, but
Yeah.
my question was that to solve for a Nash equilibrium, we'll have to solve it recursively only. Is that case?
So that's the whole point. There are two ways of going about it. Either you can do it this way, but you
Right.
might miss out on things which are called as either non-credible Nash equilibrias or
Right.
threat
The threat
equilibrias.
kind of.
Right.
Yeah.
If you want to include those also, you'll have to think of some counterintuitive ways. So either you can make similar
Okay.
arguments as before, that make a threat to choose the not rational option and maybe get a better payoff. So like push
Okay.
the other player to choose the option that is not optimal in general but is better for you.
So basically, if they ask for a Nash equilibrium, we'll have to consider both the things, scenarios, whether the threat scenario and the recursive scenario, and then see which gives the better, a more optimal thing. Something
No,
like that.
so whenever we are talking about Nash equilibriums, we are not comparing which gives us better utility. If you recall, we had seen there was this one rabbit deer version. I do not remember the details, but something like 0.5 in one scenario and maybe 2 and 2 for the other scenario. This is maybe
Right.
for rabbit, this is for deer. Let's just put these as zeros. If the two hunters sort of end up coordinating by mistake
Yes.
and choose rabbit, this is the payoff that they'll get, this is the other payoff they'll get.
Right.
So if on top of the current definition of Nash equilibria that we have, if you also say you want from those options you want the one with better payoff, then you will say this is the one. Otherwise both of these are Nash equilibrias.
Right.
The additional statement, that is to for example here, choose better payoff, that's an added thing. This may hold for certain games, in certain games it might not hold. Like, so here this was symmetric,
Right.
so we were able to make such an argument, right? But if suppose it is not symmetric and it is 1 2 to 1, now better for who? That's going to be the next question. Sure, you can try and go for a better let this be simple only. Try and go for a better payoff, but one is better for player 1, the other is better for player 2, but both of them are Nash equilibrias here. So which one will you choose? So this extra assumption can hold in certain examples, but it will not hold for all game classes. So typically, this is not considered.
Okay. Right.
By the way,
But-
since you both are asking, are there questions in the next week where they're just asking you for equilibrias without specifying which one?
No, actually, I haven't taken a look at the question. That was just
Oh,
the
okay.
general doubt.
Okay, sure. Yeah, you had a question. Continue.
Yes, I was saying that, but a Nash equilibrium might exist in the thread scenario also that sir had explained. Like, for example, if so that I'd also have to think
Yes.
that way.
Yes, you also have to think that way.
Okay.
If you recall in the lectures only, he said you can write this same game, this page is a bit messy now. You can write this extensive form of the game in the normal form, and the non-credible option that you get, non-credible equilibria that you get, which is this one, is like a threat equilibria, is actually the threat equilibria. There might be more than one,
Yes.
but that's what it would be. And the fact that this can be thought of as a threat is an interpretation. It's a very counterintuitive one, but it is an interpretation.
And these both were Nash equilibria, right?
They are.
That I
The difference is what is assumed about rationality. That is not the same in both scenarios. Here we are assuming at each stage, at every point when a player is choosing, he's rational. But this non-credible threat, the option of choosing L1, L2, that is also rational, but the rationality is not visible stage-wise. If you were to look here, player 2 saying that, you know what, I'm going to play L2, that is not a rational choice if you were comparing it recursively. But if you were comparing it in the following way, if he doesn't go with this option, he would have gotten payoff 1, 1. This is the payoff for this is the payoff for R1, R2, right? But here in playing L1, L2, the payoff that he actually gets is 0, 2. For him, 2 is anyways better than 1. So he was cleverly rational only. It's just that rationality didn't show up in the stage in a recursive manner. So those two are different definitions of rationality, which is why there is a slight confusion as to what is happening.
Yeah, but that's clear now. Yeah, thanks.
Yeah. Okay, where were we? Okay, so this example is very similar to the one that sir did in class. In fact, numbers are the only things that are different, but nevertheless. So here we have assumed both players are maximizing, which means so we get two equilibrias here, this one and this one. In and except is already a credible equilibria, so that's fine. We're getting one more, and that's going to be a threat or a non-credible equilibria, which is out, fight. Which can be interpreted the exact same way as in the lectures. So player 2 can say, or rather threaten, that if you enter the challenge, I will fight. So this is like choosing to mutually destruct. That's the threat. If player 1 believes that threat, he would not choose this option because he'd get a lesser payoff and he'll just exit the challenge. The other option is he doesn't believe the threat. He's like, you know what, let's actually go for it. I'm actually calling your bluff, and then see what happens. Then player 2 can play either of those options, because then he'll actually have a chance to play. Here he wouldn't even get that chance, and in that case he could get this as the rational output or the credible solution of the game. So exactly same arguments. Now let's take a more complicated game, meaning as in I'm just increasing the number of layers in the game. So this is one option. This is another one. This is another one. This last one is a little difficult to do in the normal form, but doing it using this recursive logic is fairly straightforward. Okay, this is a different kind of a game altogether. Okay, so let's do these one by one. Do you want to go over the arguments together? You can tell me what
Yeah,
to do.
sure.
So let's do it recursively first. Go on.
Okay, so let's say first I'll consider. Okay, so I'll start with the last one, right, of the third player, and then consider like which. Okay, so for the third player,
Oh, by the way,
so
it's not a
here-
third player, it's player one only. So
sorry, yeah,
it's okay, continue.
Yeah, so for player one, G seems to be a better option than H. So there, yeah.
So the game would
Okay.
So this is the payoff that will get pushed for player 2 to choose from. Okay, next.
Okay, and then for player two, then E is the better option than F.
Right, it's choosing between 2 and 1, so E is the better option, and hence the game will reduce to and this is going to be the payoff for E, which is 1, 2.
Right, and then here, the first player would choose D over C.
Okay, so what we got is player 1 chooses D, G, and player
yeah.
2 chooses E, or I could write it just as DG. Notationally, that just means for the first node encounter it plays 0, and for the next node encounter it plays G, if it ever gets to that. So this is the recursive version of the Nash equilibrium. Okay, now let's try doing it in normal form. So for normal form, we first need to look at the strategies for each player. So what are the strategies for player 1?
So for player one, the strategies would be the two options that he can choose, right? Like C and D, and then on the third level it is G and H.
Exactly. So it's at
So
both of these
so
nodes.
CG, CH, DG, and DH.
Yes, or you can write it as a Cartesian product between CD and GH, or your way. So either of them is fine. CG, CH. Okay, so these are the 4 strategies. What about for player 2?
Yeah, that is just E. Okay, E and F.
That's just E and F. It has only 2 options. There's nothing else it can do. If you want, for the sake of completeness, you could say there's nothing here. But that's just still, anyways, one strategy, right? Nothing more can happen. So you can stop here. That's fine. So if we were to make the normal form for this, it would be CG, CH. Right, now let's start filling it. Okay, let's start with the easier ones. So tell me what can go where.
Okay, so C, G, and E would mean then 1, 2.
C, G, E. Okay, so the first one means 1, 2.
And then C, G, F, 3, sorry. So CGF में G though is not coming. So so CGF wouldn't actually be possible, right? I mean,
It's okay,
one,
we'll
two,
come to
yeah.
that. Let's go for the easier
Okay.
ones. Let's look at the ones that
Okay.
have a clear path. So C,
Okay.
E, and H. So C, H, and E is the one that we can again fill. So this one.
Mhm.
So 0, comma 0.
Yep.
Next,
Okay, and then
that we know for sure is
DGE can okay, that's complicated, and then CHF yeah, that is also not possible. DGF D that okay, anything with D anyways no. Yeah.
Okay. So now let's look at the remaining options. These were the straightforward ones because they were clear paths here.
Yep, please.
Now, whenever we're looking for paths, we still have to consider that the other player, if it goes further, would get a strategy. So if the path doesn't even lead here, it doesn't matter. We would just go with the path that is present for us. So for example, if it is CGF, so if I'm to fill this box, CGF, if player 2 had played F, player 1 would not get a chance again, and hence will have nothing to choose between G and H. So that part won't matter. Which means here the payoff is decided and it's just 3, 1. So I can fill this as 3, 1. Now, if G was instead H, same thing happens. That path never even happens because with F it ends, and from F onwards there is no further option. So this is just again 3, 1. Right?
Yep.
The point here is these strategies may not all be reachable from every node. In the process of writing strategies, we've written the whole plan. If the player reaches a so-and-so node, then this is to be done. If it never reaches there, then we go with whatever payoff we got in the path that we reached. So that's why some values get repeated. Okay, now we can look at the last option, which is D.
So that would be 2, 0 only.
Yes, that would be 2, 0 for this whole block. All of these would just be by default 2, 0. So this is 2, 0. And now we can search for threat equilibriums.
Okay.
Interpreting those would be a little harder, but doing it from here is not that difficult. So this is one. This is the second one. This is the third one. So what all did we get?
Okay.
Here, you can verify if you want.
Yeah, actually, I can't see the diagram half the time, and then this because I know you're focusing on this. So I'll just draw it quickly, maybe the diagram in my notebook.
Yeah. When we are doing it from normal form, just look at the normal form itself. Give me a minute. I need to charge my laptop.
Can you scroll the screen?
Hello? Okay, am I still audible?
Yeah, we can hear.
Okay,
Yeah.
so let's continue. So we got 3 equilibrias here, and those are E, DG, E, DH, and last F, CH. So this first one, this is credible, so this is okay. But it's these two that are not credible. These are the threat equilibrias.
So how did you calculate the equilibria in the normal form?
This is what it did. This is the normal form, right?
Yeah, this is the normal form, and we wrote these numbers. But then, how did you
Oh.
go about calculating the
Oh, so-
equilibria?
So whenever I get a matrix, I do it in a very quick manner. So for example, let me repeat the process. You can either make the arguments verbally, or you can note them down on the matrix itself. I prefer noting it down because then chances of forgetting something are a little less.
Mhm.
So what is to be done is both the players are maximizing, right? So
Mhm.
for player 1, before he has to choose which of the actions or strategy to go for, he will go through all the options of the other player. So he'll fix a column and go through all of these options and note the ones which have the highest payoff for him, or maybe the equal ones. So for that, it's these two options. So DG and DH are good choices, focusing only on column where player 2 plays E. On the other hand, if player 2 plays F, by the way, I'm comparing utility of first.
Okay, got it. Got it.
Similarly,
So
for the other,
if player 2 plays E, then for those four, 2,0 are the better options. That way. Okay, and if it plays F, if player 2, if player 2 plays F, then in that case, yeah, 3,1 are the better options. Okay.
then same arguments for the other player, which says that okay, because these two are anyways the same output, so there's no deviating or anything. So this is a Nash equilibria. For that same region, both of these are turning out to be equilibrias. And this is the proper one. Okay, so now let's, this one is credible, so we are okay with this. DG comma E, yeah. Now let's look at this option. Now notice, player 1, the credible option says player 1 plays D, meaning the game never goes on this side of the sub game. The game actually just stops here. After playing D, he gets a payoff and the game is actually over. And yet, he's still looking at what is the best option from the two. So here he said, okay, the best option between G and H is G, hence G is chosen. The best option, having chosen G here, would be to look at these two payoffs and choose again this one, meaning E. And that's how we got this choice. But this is something that never really happens if player 1 has already played D. Meaning, this is actually still okay. This one is saying player 2 plays E, and player 1, when it's playing again, instead of playing G, it plays H. So here is the part where it's not rational. So in some sense you can say, in comparison of these two, this is the irrational choice, and this can be thought of as a threat, which when goes upward makes this as a better choice for player 2. So player 2 is now forced to choose F if it gets here, but player 2 can also be irrational and say, okay, I am going to go for E, and that's what forces one to choose this one.
Oh,
So it's
okay.
actually an equal choice, because here otherwise he would have had 0, 0. Oh no, it's not an equal choice, right?
Actually, there is 1, 2, and there is 2, 0. So I think it would still be better for player 1 to choose. Acha, haan, nahi, for player 1 to choose D would be better. Yeah.
Because here, if it does percolate upwards, so it would be this one and then this one. So here it would be left with 0, 0. Between 0 and 2, 2 is better. So that way it's a fair choice, but it's just pushing it in a certain way. So this is definitely a threat kind of an equilibrium. Let's look at this one. So this is F and CH. Again, player 1 threatens to play irrationally and is saying, okay, if I'm at the last node, let's give these nodes some name, X, Y and Z. So at Z I would play H. With that threat, if player 2 chooses to be rational, which is to compare 0, 0 with 3, 1 and choose 1, he would have chosen F. If he had chosen F, player 1 would have had the choice of 3, 1 with 2, 0. And player 1 then would be like, okay, then D is not a good choice, then I should go for C. And hence, this is the option that's coming up. And it's coming up because player 1 himself threatened. And in this process of threatening, the outcome it is getting is actually very good for player 1's perspective. Player 2 is getting 1. That's not the best it could have gotten, but anyways, it's still okay.
Right.
So that's one way to sort of argue about these kind of problems.
Okay, understood.
Understood? Okay. So let's try another. Let's take an example of this kind. So this is a much bigger example. Let's do it recursively first and then we'll do it in normal form. So if we were to do it recursively, we would start from the bottom. Player 1 would choose. Yeah.
That matrix we have extension form. So through that, how we can find the backward induction?
Okay. Well, you can take this as that example, how to go for backward induction. So we're doing that.
Okay.
So backward induction means you're starting from the bottom. This is a easy game, meaning it's a perfect information game. Everybody knows everything, or everybody knows like what happened before them. So that way it's a perfect information game. This would become more formal in the upcoming lectures. So here what you're doing is you consider the player and just see which of those two options, between the options it has available, which is a better choice at that stage. So over here we'll start from the back. So here player 1 chooses. Player 1 has 2 or 1. So it would prefer G. Now player 1 has already chosen rationally, meaning this choice will get pushed here. So the new reduced form of the game would look like this. This choice just got pushed upwards. Then same argument is going to follow, but now player 2 is actually making choice at 2 different nodes. So for each of those nodes it's going to make its choice. So for this node it's going to choose between 8 and 3, and hence it will prefer this one. And for this second node it will choose between 5 and 10 and end up preferring this. And both of these options will get pushed upwards. So this got reduced when player 1 played G. Now this is getting pushed when player 2 plays C, F. Okay, it's at different nodes, so we have to specify what happens at each node. That's what's happening here, which means this game now becomes player 1 has option A and option B. Option 1 would give him payoff 3, 8. Option 2 gives him payoff 2, 10. And now he has to choose between 3 and 2. And he would choose this one. So what happened here is So let's write for player A first. Player A at the highest node, sorry, player 1 at the highest node will play A, and the last node it would prefer playing G. So AG comma B, this is the credible Nash equilibrium.
AG comma B. So it's
Yeah, how you have
it is
written?
both A and B.
Hmm?
Uh,
Oh,
for
okay. What did I write?
G is correct, and
Yeah, I've written it wrong. So G is correct. A is also correct. This should have been CF.
yep.
So AG comma CF. Yeah.
How this GA?
So what is actually happening in recursive choices at each level, you're choosing what is the best option from the ones that are available. So if the game were to go from here, so if player 1 has played A, then what would player 2 prefer doing? He would be choosing between C and D, and between those two options C is the better choice. So this is okay, right? Now if suppose player 1 had played B, strategy means it needs to create a plan for whatever action is taken by first player, right? Meaning it will also have to consider this option, that player 1 has played this second thing, which is B, then what would player 2 do? In that case, player 2 has to choose between E and F. But the actual choice between E and F depends on what got percolated upwards from here. And that, if we are assuming player 1 is still rational, we can expect he would choose G, and the payoff here would become 2, 10. And hence, between E and F, player 2 could say the better choice for me, assuming player 1 is rational even afterwards, the rational choice for player 2 at this node would be to compare 5 and 10, and 10 is more, and hence F is the correct choice. Now when you look at the game, in the game it's only a part of the strategy that's going to get played out. The whole may not always play out. If suppose this was one equilibria, even then we would have a choice between C and D in our strategy itself. Like it would show up in the description of the strategy, and that's pretty much why we have this F showing up or G showing up here. And okay, hold on, if it's still not clear, just wait a little bit. We'll write down all the strategies in this game, and then this will make a bit more sense. Okay, so now let's write down the strategies for both the players. So let's say the strategy space for player 1. Vivek, why don't you try and tell me what would be the strategies for player 1?
I have no idea. I forgot how to write the strategies.
Okay, no problem. So when we are writing strategies, remember in extensive form, there is a possibility of repeating also. Like one player can get more than one chances to play. So we have to consider every time he gets to play, we have to consider all its action choices available. Okay, so we write it for each of those nodes where player 1 gets to play. So player 1 is getting to play here and here. So at the first one, the options player 1 has available are A and B. Right? At the next node,
Yeah.
when it's A's turn to play again, the actions it has available are G and H. So this is the whole space of strategy for player 1. You can either write it as a Cartesian product for each node written separately, or you can write it together and you can write it as AG, AH. So this would be the whole thing, BG and BH. This is the plan. So the plan is specifying, if I am at the first node, what am I choosing, and if the game ever gets to the next chance player 1 gets to play, then what am I choosing? The plan, the strategy needs to have all of this information. Even if the game never gets here, he needs to plan according to, with the assumption that it might. So this is like a contingency plan, that even if that doesn't happen, I should still prepare for it. Okay, so these are the options available for player 1. Now let's look at player 2. The strategies for player 2 are, what are the strategies for player 2? Now give it a try.
C, D and E, F.
Exactly. Or if you were to write it properly, because those are at different nodes, right? C, D is at one node and E, F is at a different node. Then you would say there are 4 strategies, but the strategies are to be written in this way. It's either CE, CF, okay. Remember, strategy means it's a plan for what to do at any node in the game where the so-called player is playing. The plan cannot suddenly not have any response at a certain node. So it should include both of those informations. Here it's playing at 2 nodes, so
Right.
both of those. Clear?
Yes.
So that's partly why with C we had something else, with G we had something else. You can see GA is one of the strategies. AG or GA, doesn't matter how you write it. CF and is one of the strategies of player 2. And that's pretty much how we have written this equilibrium.
That makes sense.
It's just notation.
Yeah,
nothing else.
clear.
Okay, so now let's make the normal form for this. This is not gonna be easy. There are 4 options for player 1. Okay, so now let's try. To fill this, let's take the easier ones first. In the previous ones, at least some of those could be filled without having to think too much. Here we will have to think for pretty much the whole thing, but let's still take the easier options. So let's say when player 1 plays A followed by C, the payoff is 3, 8. No matter what was suggested here and here, right? Because these are not happening, so the payoff stays the same. So
But in the case of, let's say, AGCE, so in that case, okay, makes sense. Yeah, right. Got it. It will be A and C only.
so that's still 3, 8. Because the G part or the E part, this is the contingency. If the players were to be in such a way that those were accessible, those were actually playable, then those should be played. Okay. Next, AG CF. Now see, this is A G C F. There's still one path here, and this is that. So 3, 8 is still it. Similarly, let's try AGDE. Is it doable? Okay, it's still fine. So AGDE. Now this is the path AD, which leads us to 8, 3. What will happen in the last entry in this row?
That would be AD again.
Yeah. So
8,3.
still 8, 3. Okay. Now, even if I change G to H, so here I've changed. Will these entries change?
No.
No, right? So this would be 3, 8. This would be 3, 8. This would be 8, 3. Okay. So we have finished what happens with A. With B, it'll be a bit more interesting. Okay. So let's go with B, G, C, E. Now C will not get played. The one that will show up will be either E or F. So that's the one that's going to matter. C and D will not matter in this because that is not in this path. So D, C, B, C, E, and G. So the path that shows up is this one. This is 5, 5. And in fact, BH would lead us to the same thing. So this is again 5, 5. Now let's take the next one, BG, CF. BG, CF. Now see, the paths that came out is this one.
2, 10.
Exactly. So this becomes 2, 10. What will happen for the next entry? BG and DE. It's
5,
5, 5.
right, it's 5, 5. And last one, BG.
2, 10.
Exactly, 2, 10. Okay, next. And this is
1, 0.
exactly BH,
Yeah, 1, 0.
CF. So 1, 0. Next,
5,
5, 5.
and last.
1, 0.
So by this point, you've at least understood how to create these matrices. Once you have
Yes.
created it, you can find the Nash equilibrium. That is something that we've been doing for the last few weeks, so that's fairly easy. So in this
Okay.
example, everything is maximizing. So I'll do it my way, which is comparing column wise, keeping a column fixed and looking through different values in the row. And that part is done. So now for fixing a row and looking through the column values and highlighting the maximum one. So we got 3 options here again. These options are one is AG, comma, this is AG comma CF. That was the credible Nash, so that's already okay. We got two more. One is AH comma CF, and last one is BH comma CE. So these two are the thread equilibria. This is what we got from recursive process also. So now let's try and interpret what these mean. So AHCF. So first part of the argument could be, because there are only two options and player 1 is choosing H, meaning it's sort of a threat or a promise. So player 1 goes with this, meaning player 2 now at this node has to choose between 5, 5 and 1, 0. It depends what player 2 is going for. If player 2 is planning to be irrational as well, it would choose 1, 0. So here 1, 0 gets populated till the top. Here, okay, here he's not being irrational and he lets it be 8 only. So this is the one that comes up. So it's a comparison between 3, 8 and 1, 0. And player 1 would choose this one. So the path is AC, ACFH, or rather AHCF. And what happened in this particular process is player 2 did something very unexpected. It was rational at this stage, but it was rational at one node, but it was not rational at the other node. Player 2 actually did the same thing, was irrational here but rational here. And in the process of doing that, what happened in this game is, so for this one the payoff turns out to be 3, 8. And that's the same payoff from here also. So at least the payoff is not changing. The only thing that is changing is at certain nodes the option is not the best one from that portion or from that subgame. Okay, so let's look at this last option, BHCE. This is BHCE. This is pushing for both of them to get 5, 5. So again, player 1 threatens at this node to play 1, 0. Once it has done that, it is to be chosen by player 2 as to what to do. Player 2 goes for the rational choice. Player 2 picks 5, 5. Here again, if it is the rational choice, that is 3, 8. So between 3, 8 and 5, 5, player A would prefer 5 over 3. And hence player A at this node, being rational, would choose 5. And what in this process, what player did was, in the process of being irrational at this node, is he made his own payoff increased, and it now became 5, 5. Okay, so the idea is that if we were to restrict ourselves by saying that the solution concept of these games has to be recursively rational, or that at each state the player must choose the most rational option, then the equilibria that we are getting point number one, there will always exist one such equilibria because we are finding it from the one path in the game. So there will always be at least one such path. And point number two, this Nash equilibria will exist even in the game where we allow there to be threats or promises, and we look at the normal form version of this game.
Right.
Okay, we could repeat the same process for a lot of other games. This is one of them. This is, I think it's called a centipede game. It's a very famous one. Now you can see this is an extremely long game. If I were to write out all the strategies and look at what happens in the normal form game, it will not be possible to analyze it properly because the number of strategies is going to be quite large. But we can still analyze what happens in the recursive rationality scenario. Okay, so let's do that. There are just two players, player 1 and player 2. This one is player 1. Player 1 starts. He's either supposed to stop the game or continue. If he chooses to continue, his payoff reduces by 1. But for the other player, the payoff increases by 3. Same thing the next player also gets to do. If the next player continues, his payoff reduces by 1. And the payoff of the other player increases by 3. And that sort of continues. So in this type of a game, if we were to argue by induction or backward induction or with recursive rationality, what should player 1 do? And if you can say, what should player 2 do? The way to argue for this game would be same as before, to start from the back. So if we start from the back, this is comparing these two utilities of player 2. This is better.
Yeah.
So that would mean this becomes the utility at this stage. So player 1 would compare 98,101 with 99,98. So player 1 would be comparing these two. So between 99 and 98, he would choose 99.
Hmm.
You can continue the logic, and that will tell you player 1 plays S at first step. If he does that, there's no further game. You can have a strategy here, but the game is actually over before it even began.
Right.
So assume that's not what the first player did. Let's say the first player decided not to end in the very beginning and wait it out and continue. Let the other player do whatever he wants and then continue. If he had continued, so if we compare this with this, his payoff is increasing. But in the process of comparing recursively, we are comparing only at one stage, at one node, what are the two different outputs, not between two different nodes. Right? Same thing was happening here also. The comparison, if we were to do recursively, led us to this point. But there is one equilibria which led us to this, which is actually a very good option from player 1's perspective. but this would be comparing two different payoffs at different nodes. And to be able to do that, he has to make certain irrational moves at certain stages. So the point of showing this game is no rational player in the truest sense, like a player who has access to this whole game, would look at it and be like, you know what, I'll quit at the first step already. No player would prefer doing that. The players would prefer going at least somewhere forward in the game and then quit. But the catch is, at some point they'll choose to be irrational. Only then they'll be able to go somewhere further in the game. If we were to argue it properly, from the backside, some player would, at some node, he would decide to be irrational. So maybe he decides to be rational here, so choose this. But maybe here he decides to be irrational. That okay, between these two, the better choice is, even though this one, I will choose this, because this payoff of 98 is better than a payoff of 1 that I would have gotten at the first one. By being irrational, he might force the other player to also be irrational, or the other player might still continue to be rational. If the other player continues to be rational, the player would have ended it already over here, because player 2 would be comparing these two. So there is like
Right.
a in-between way of thinking about rationality also, or more like a behavioral situation is also possible. So the solution concepts, both of these solution concepts, where we either consider recursive rationality, or if you have some background or are aware of terms like greedy, this is a term typically used in computer science. So if you were to be greedy at any stage, you would pick the best one at that stage and then go in the next stage and choose the best one there and continue. But it can always happen that through the path, that suppose this is the path that's chosen, what you're getting is not the overall best. It's like a local minima but not the global minima. But for okay, so yeah, so the last point that I was making over here was these two ways of thinking about rationality, one in a recursive manner, which is actually a greedy choice, which is that you're choosing the best at that stage, versus looking through the whole matrix and choosing options which may seem counterintuitive, like either this option or this option, or for example in the centipede game, something in between. But if overall payoff is what we want to improve, then this is in a way a better choice. That being said, in this course we'll mostly be talking about these two kinds of rationality only. One is the recursive one, or equilibrias which are called subgame perfect equilibrias. So for example, this one is subgame perfect. And these would be threat equilibrias. Okay. I had one more example, but this was not properly covered in this lecture, so I don't want to say much. But just for the sake of making a statement. So if we were to genuinely be able to compare this extensive form of a game with the normal form of a game, we need to make it very clear whether the actions are seen by the players or not, whether the action of whoever played before them is visible or not. Because if it is visible, then that's in principle an extensive form, just represented as a normal form. On the other hand, if we want to represent a normal form game, an actual normal form game of this kind, for example, don't worry about the numbers, where the players have actually don't know what was played by the other one, then we need to mention that this player 2 doesn't know whether L1 was played or L2 was played, or that these two actions lead to something that's called an information set, or that these two actions are indistinguishable. Then the same form that we are talking about, the extensive form representation, can be used to talk about games, simultaneous games as well. Once we have done that, then whatever arguments we've been making so far can be made more concrete. Because here what we have done is we have compared this kind of a game, which is a normal form game, which is an extensive form game, with this game which is in reality a simultaneous game, where this strategy doesn't necessarily say if something is reachable or not. It's all it's saying is there is a strategy like that and the players are just going ahead with it. That's an action, that's a plan, and they're going ahead with it, and that's all. Okay, so with this I'll leave this example for maybe next time once we've covered information sets. So with this I am done with the tutorial. Do you have any questions?
I just wanted to thanks for the session, by the way. It's very helpful to me. And I wanted to ask if there is any book that you would suggest that I can read and also use for solving questions other than these. I mean, in general.
So there are some references in the description of this course. One of them is I can never remember the full form. It's MSZ. There's a game theory book, MSZ, by the authors MSZ. One of them is Michael something. If you look at the list, you'll know which one I'm talking about. This is one option.
Okay, sure.
The other is Meyerson, a game theory book by Meyerson. This is very readable. So all of these arguments that we keep saying in words but don't write all of them, you'll see a lot of those are written. But Meyerson does not cover all the topics that will be covered in this course.
Okay.
MSZ is slightly more formal throughout. There is one more book by... okay, I'm forgetting this name. Narihara, I think.
Yes.
This is game theory and algorithmic design, I think.
Yeah, he's a very famous professor.
Yeah, this is the IISc professor. This is also a good book.
Okay. Right. And does this cover questions also, or mostly the read?
There are a lot of questions. In these two books, you'll find a lot of questions. Meyerson might have a few, but he goes in complete depth of those questions. So even if it's just a few questions, you'll still get a very good idea.
Okay.
In fact, I think some of the questions that I took today, these ones, this one or this one, these are from Narihara only.
Okay.
Yeah. So yeah, I would recommend you can have a look at these books and see which one suits your requirements.